try to recuperate. All right, I'm not sure exactly, to be honest with you, where I left off last time. So, but I'm going to just kind of go back to scope rules. I don't think I covered this very well if I did cover this discussion. But this particular one talks about the fact that we've got 4 ways that we can declare a variable. And what that gets into is where this variable is recognized. That's there. And when we get into this idea of scope, find one over here, right there. This is our, and it says setting up a pin right there. This is our file right there. Right there. And right there. And if I declare a variable, say int I right here, and here's main right here, and the beginning of main, here's all my other functions. If I declare this outside of main, this is a file or program level variable right there. So as we get into this whole thing is we've got file scope. And all right, I was hoping the update fixed that, but it didn't fix it. File scope means that it's known to every function within that file. So if I use I and I change it anywhere in any function within the file, it's going to change I. Then we have function scope. Function scope basically means that if I have a function, say int square right there and int x right here, and I declare int y inside that function, and I say y is equal to x times x, and return y, and I apologize for my handwriting, it's just bad. Return y right there, and there's my end of the function. This y right here is only known within that function. So if I have a y somewhere else in my program, it doesn't change it. It only changes it when that function, when this function ends and I go back to x, or go back to main, or wherever I call square from, y disappears. It's no longer there. So that's referred to as function scope. A block is, for example, if I do a for loop. For and int I equals 0. Now I don't know what, I got this some funky mode right there, and I is less than whatever, and I got there right here. This I is only known within this block here. It disappears as soon as I end the block right there. That's what's called a block scope right there. So, and then function prototype scope, I won't talk about that much in there. So that's it. Now we can use labels right there, and labels are, if we're going to do like a goto or something like that, we in C and C++, we typically don't use labels very much. That's normally used in more in other languages. You can use it because you can use a goto statement in C, but nobody teaches it. It's considered bad programming right there. So, well, except for in labels, except for in the switch statement. I forgot those are actually considered labels up there. So, up there. But The only thing I'm really concerned about is knowing function scope, file scope, and block scope. Those are the three that are important. The function prototype scope, not too much. I don't worry about labels, even though they're technically labels within a switch statement. I don't think of them as labels. Right there. That's it. So that's it. So that just basically covers everything that I want to cover about scope rules in a very short there. And you've seen them used in different places there. So again, global, we often refer to as variables that have file scope as global variables because they're known everywhere. And then we often use the function variables as local variables. So you'll hear those two terms used a great deal. So again, blocks can also contain. This is a tricky one right here. This one's tricky. If we nest blocks and we use the outer block has the same name as the inner block, the outer block is hidden. So we could use the same variable twice, and it's even though we're within the main block, that gets very, very that there. An example of that would be for I or int I equals 0, I less than 10, I plus plus, and I'm just going to do a printf. And as I said, I'm not feeling real well. One of the things that happens when I get tired is my handwriting gets worse. Right there. %d/n I. And then I turn right around and I put another for int I equals 0, I less than 5, I plus plus. And I do a print f blah 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 blah, and put a semicolon at the end of this right here. I'm going to put a bracket here and a bracket here, close a bracket here, and close a bracket here. This is one block right here. That's a block. This is a block. So I've got a block inside of a block. I use in the inner block a block level variable I that's the same as the block level variable on the outer block. So I'm using I twice, but it has a different value within the inner block as it does the outer block, because once I go into the inner block, I is hidden. It's put back in the background, and we have the new I inside. And then when we leave the inner block, that I disappears, and the I that's defined here becomes the value of I. So now I, depending where I'm at in this block, has two different variables, or values, excuse me. Very, very, and pardon my French here, freaking confusing. I would suggest that you would name the second one J or K or L or something else. Use a different name. Don't reuse the same name. You can do it. Some programmers have no problem with it. That they're keeping track of what the value of I is a pain in the neck. Especially if you're using some kind of debugger, because then all of a sudden, which value of I am I talking about? Which that's it. It's bad enough when these variables are block level, and it gets even more confusing if I've got int xyz, the name of the function, whatever that there, and I have int I as another value. Now I can have three values. It has a function level value. It has two block level values. So you can see very quickly how C can be very, very difficult to use if you don't keep your programming easy. That there, you can really, really complicate what's going on. So this means when the blocks are nested, an identifier in the outer block has the same name as an inner block. The identifier in the outer block is hidden until the inner block terminates. In other words, the original value of I is lost. That means when it sees its own value, not the value that is identically named in the enclosing block. So that's there. So it just gets very confusing. I would not do, personally, I don't do block level declarations. I only do function level declarations. It solves the problem. I don't define I within a for loop, for example, typically, or a do until loop. That's there. So now we also have another word that is called static. And static means that it will keep its value from call to call. So if I declare a variable as static and my function ends, the next time I call that function, whatever its value was before is restored. If I don't use static, then it's redefined as whatever I initialize it to. I typically don't use static unless I have to, and you'll know when you're forced to use static. That's there. So storage duration doesn't affect the scope. I won't get into that. So only identifiers with function prototype are those listed in the parameter list that there. Again, I skipped that. Programming error accidentally using the same name for identifier in the inner block as inner block when the outer block to be active here. All right. What they're saying, for example, when I use the nested loop there, where I add an inner block and an outer block, that one of the things happens is you try to use the old value of I within the loop, and it doesn't work because it's been wiped out with the inner value. That's why I don't like to do that theory. Again, if you don't reuse variable names within blocks, you don't run into this problem. Avoid variable names that hide names and outer scopes. That's there. In other words, again, I get around that problem with just using function level variables. I don't use block level variables. That's there. I just don't. So this kind of gets into the whole issue here. This is an example, some examples. I'm not going to go into this in much detail, but here we declare a variable of x. Here, this yellow part right here, this is a block right there. And I don't have to have a for loop or until loop or a function call. I can just put a bracket anywhere and close a bracket, and that forms a block. So now I set x and I equal to 7 right there. I end that, and outside of it, as soon as I hit this closing bracket, this x disappears, and then this one comes back. So in this particular case, I've got x used 3 times. It's declared as a global variable, it's declared as a function level variable, and it's declared here as a block level variable. So within the function of main, x is equal to 5. Within this block, it's equal to 7. And then right here in main, and then here on local, I now have it now equal to 25, right there. So now there's 4 different versions of X. You can see how complicated life can get. What does X equal? Well, here it's equal to 5. 5. Here it's equal to 7. Somewhere it's equal to 1. I don't know where. There's probably another function down here. Here it's equal to 25. Right there. Here it's equal to 50. And so now it's got another value. And here it's equal to 1. And then, of course, I'm multiplying it by 10, so it's going to be equal to 10 as soon as I'm done with this call. So you can see where, I've got one variable, X, and it's got how many different values within my program. At the global level, it starts out equal to 1. Within main, it's equal to 5. Within use local, it starts at equal to 25. Right there. Within static local, it's equal to 50. Right there. And then every time I go through a call use static local, it's going to increment it, and it's going to remember the value right there. And in use global, it's going to be equal to 1 the first time, and then it's going to be multiplied by 10. So again, you're seeing right there. So it's equal to 5, then 7, then it's X. Then it's equal to 25, but then we increment it. It's equal to 50, and then it's equal to 51. I call use local again, it's equal to 25. The value is not kept because it's not static right here. Use local, it's not static. So the next time I call it, it's going to be reinitialized back to 25. But in use static local, the first time I called it was 51. The second time I called it, there was 50. I increment to 51. The second time I called it, it's now equal to 51. It goes to 52. And then use global, it's equal to 10. That there, and then it's equal to 100. That there, again, because it's the global variables are always static. Right there. So it gets into a very confusing, the scope rule, but it's one of those things that you have to keep track of, right there. And as I said, I was going to keep things relatively short. This is the end of the chapter. Now we're getting into something that's even more confusing. So today I've got 2 confusing topics right there. Recursion is a function that calls itself either directly or indirectly. Right there. So in other words, a function that just simply returns back the same function value, or a call to the same function. Right there. It's one of those things that is discussed at great length at the upper level. I've done a lot of recursive programming. That's it. But recursion can cause some serious problems if you're not careful with it. And you got to be careful. At this level of programming, you probably should avoid recursion. And the way that most people do recursion at the starting level without getting into things like linked list or binary trees or bin sort or some of these more complex algorithms is they do a max out. Right there. So this is going to give an example that's a relatively straightforward example right there. And this book contains extensive spread through chapters right there, summarizes right there. I'm not going to go into these examples right there, but I'll just give one example right there. It is returned with a base case at there. Complex. Make recursion simple because you have to have a way out. This is a whole text at there. So the simplest version, and hopefully they go through the example here. Looks like a original problem, calls a fresh copy itself to work on the smaller program. So it's a recursion. And I'm going to just kind of jump. Oh. Oh. What happened? Right there. Must have closed it. Okay. Let's look at the case of 5 exponent right there. Now that's equal to 5 times 4 times 3 times 2 times 1, right? That's the exponential right there. Right there. Or factorial, excuse me. 5 factorial right there. Now what I can say is that 5 factorial, first off, before I do this, right there, is 4 factorial is equal to 4 times 3 times 2 times 1, right? 3 factorial is equal to 3 times 2 times 1, right? So I could say that 5 factorial is equal to 5 times 4 factorial, right? So I could write a function to calculate the factorial fairly easy by saying int fact, I'm going to call it fact right there. I'm going to receive an integer x right there. And I'm going to simply say if x not equal 1 right there, return factorial return, I made a mistake here, x times factorial x minus 1, else return 1 in the function. Very simple function right there. But what I've done here is I've created a function that takes fact, let's pick a different color, fact, and I called it within the same function right there. So this allows me to look at the function, or call the function. It's very simple right there. And it's a very, very easy example of recursion. The problem with recursion is that you have to allow the escape button right there. The escape, in this particular case, is right here. This is the escape mode right here. If x is equal to 1, we're going to return 1. That there. So each time I call fact, it's going to have a value. First time I call it, I pass it 5. Then I'm going to pass it x minus 1, so then I pass it 4. So then the next time I call it, I pass it 3. Then 2. Then finally 1, and then it backtracks its way back out. Right there. So what we do is, we're calling initially fact 5, which then turns around and calls fact 4, which then turns right around and calls back 3, which then turns around and calls back 2, finally calls back 1. Now once it gets to 1, it's going to then return 1. So then it goes back here, and this got value, when it returns that, it's going to return 2 back to here. And this is going to turn right around and pass 6 back to here. This is going to turn right around and pass 4 times 6, 24 back to here. And then this will return the value 24 times 5, which is 5 factorial. So this calculates the factorial by using something called recursion. Now, recursion is used a great deal when you're dealing with things such as a linked list. A linked list is something that I've got a pointer that points to the next item on the list. And then finally, I reach the end of the list, and this points to something called null. In other words, there's nothing there. And if I want to add something to the list, I just traverse to the end of the list till I see null. I create a new node and make this null, and I put my new data there. So I just simply add it to the list. Then I just simply keep traversing the list by add to list. And I pass it to the next node. That's more advanced than we want to get into in this class. That's there. We also can do what's called a binary tree, where we've got, here's my data, and I got a pointer to each side, and I generate this where the tree is always sorted. These are more advanced. They use recursion. So recursion's used a lot. Right there. Right there. But it's really something more advanced I want to get into. But it's something you need to be at least aware that it does exist. Not all languages allow recursion. Right there. But for recursion, each time the function calls itself with a slightly simpler version of the original problem. So the whole idea is we make the problem simpler by that there. So when it recognizes the base case, it returns back. So our base case in this particular case is if x is equal to 1. That's there. Otherwise, we just call factorial again. And again, they go through the same example right there. And here, this is non-recursive method, where we go through a loop and counter is equal to number. If counter is greater than or equal to 1, counter is plus, and we just multiply it each time through there, right there. And again, this is the same thing that I just did right here. And we return number times factorial number minus 1. That's just the same example as I did right there. So slightly simpler file. And we just keep doing that. We keep doing that until it's equal to 1, right there. And this is just kind of a nice, neat little sequence. 5 is equal, factorial is 5 times 4 factorial, which then is 4 times 3 factorial, 3 times 2 factorial, 2 times 1 factorial, and 1 factorial, of course, is back to 1, and we're going to return right there. And as you can see, this shows values as I did talk about right there. So it's a very powerful tool. The first time I had to do it, I think I was taking a Pascal programming class, we had to do something called the Towers of Hanoi, right there. And the Towers of Hanoi is a classic computer science example where you've got 3 pegs right here. And I've got 4, I'll show 3 right there. And I want to move them to here. right there. Well, the way I do that is I first move this one to here. Right there. So I have, the starting peg, the ending peg, and the off peg. And I just keep calling the same routine until I remove the final peg. Right there. And you can do an online search for Towers of Hanoi and find the program. It's more complex than I want to get into, but it's a way of solving this problem. And I don't know if it's a children's game typically where you've got the three, you want to move them to the, and it's a classic example. It's easily solved using recursion. Easily solved. If you try to find a non-recursive solution, it's very difficult. Right. So again, this is the same one where this actually, for each iteration, and we're calling from 0 to 20, 21, factorial I, and here's our factorial I program. It looks exactly like what I did right there. If number is less than or equal to 1, return 1. Otherwise, return number times factorial n minus 1, or number minus 1. So it's, again, the same example as I just did. I didn't realize that they were doing this example. Otherwise, I would have not gone through and maybe suffered through my bad handwriting. But it's the same example as I just did. And as you can see, this just keeps that there. It's a relatively simple program to show recursion. That's there. And this just kind of explains it. And again, even if I use unsigned long, I'm going to blow out of memory. That's there. That's it. Points of weakness in C's and most other is not each up there. Skip that particular discussion right there. Common programming error. You forget the base case, if x equals 1, return 1 right there. Fibonacci series is another example right there. And that means that 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5. It's the sum of the previous two right there. Again, we can write right there. Again, this is Fibonacci n is equal to Fibonacci n minus 1 plus Fibonacci n minus 2. Right there. It's another example of how we can use recursion. Right there. And this just shows right there. If it's equal to 0, right there, and we always start out with 1 right there. So Fibonacci 1 is 1, 2 is 2. Fibonacci 2 is right there. And again, we're looking at the fact that we can just go through and write the Fibonacci. And I think that kind of lines up this example right here. Again, I'm not going to make you write any recursive programs. I just want to introduce the concept of what it is. If I had a final exam, then I probably would ask you to find recursion and give an example, and I would expect the example of factorial or Fibonacci, the two that are given. Those are the easiest two to show. The Towers of Hanoi is a little bit more difficult right there. And I think that kind of wraps up this right there. This explains more about the Fibonacci series. Again, I'm not going to get into this. Both are based on control. This just simply compares the two. Most more advanced programmers tend to go for the recursive route. There is a problem with the recursion route, is that every time I call a function, and I kind of skip this discussion, the variable that I'm passing to the function is pushed onto the stack and what's returned back is pushed onto the stack and popped back. So if I call something that's recursive and it calls itself many, many, many times, and my stack size is large enough I can have a stack overflow error. With desktop computers, that's not necessarily a problem. Embedded systems, you have to worry about how big you make your stack right there. So you could run into some problems with stack overflows if you use recursion, and it's a very, very deep recursion. When I say deep recursion, if I ask for the Fibonacci value of 650,000, it means it's going to have to call Fibonacci, it's going to have to call itself 600 and some odd thousand times, which means that it's going to have a half a meg of available memory to retain return addresses and values, because the return address has to be pushed on the stack too. So that's more of an embedded systems problem. Desktop computers, now the smallest desktop comes with what, about a gig of RAM, 2 gig of RAM. You're not going to really blow out a stack size with that there, but it's one of those issues that embedded systems we worry about up there. Recursion has many negatives that there. Again, repeatedly invokes, and consequently the overhead of function calls. The overhead of function calls is that use of the stack that I was just talking about. So recursion is actually a little bit slower and uses more memory than not using recursion. But sometimes it's easier when you're solving a problem to think about it in terms of solving it using recursion. Some problems you have to use recursion right there. So each recursive call right there, and why choose right there. And there's that figure 521 in the book gives 31 recursive examples in the text that there. So if you look at the textbook, it has lots of examples where recursion is used right there. And again, notice that I mentioned the first one was the Towers of Hanoi. That's listed as one of the examples. So you can find that example there. And that's there. Chapter 12, which we won't get into, is linked lists. I talked a little bit about linked lists as an example right there, in binary trees right there. Chapter 6 is printing an array and printing backwards linear search. So there are some examples we'll look at in the next chapter. We're probably going to be stopping in chapter 7 or something like that. So we're only looking at a couple more chapters I'm going to finish, and then we're going to move to MATLAB. Right, so obviously I'm not going to get into chapter 12. Right there. So again, where do functions put out there? This is just, I think that kind of, and again, secure programming, we're not talking about that there. And again, when they talk about the fact is that RAND does not, this whole discussion talks about the RAND function. They're pseudo-random numbers, not truly random. If we want true random numbers, we have to use the cryptology random function, and that's beyond the scope of this class. All right, I talked very quickly, and as I said, I was going to end early today. You've still got, I think, the one program you're still working on, right? One you're supposed to submit, and then the other one you're still working on, so give you a little bit of time to finish that up there. We'll start up with chapter 6 next time there. And I assume we'll meet on Wednesday. I guess next Wednesday we don't have class. Is that true? It's Dipavali next Wednesday. That's there. I think we have a holiday coming up in the middle of the week. So don't you just hate holidays in the middle of the week? You'd rather have them on Monday or Friday. But because no one can go home for the one-day holiday. But so with that said, I'm going to kind of as I said, I was going to finish early.